Salt. Fast food chains, halophiles, and internet trolls all love it. But have you ever wondered how salt can be used to prove that the first n positive integers sum to n times n plus 1 over 2? Well, stay tuned to find out. Okay, so let's call the sum of the first n positive integers s sub n, or Sn if you will. Our task is to find a formula for this sum. Before we use salt in our pursuit of such a formula, let's start off by finding it in the most common way that you might have encountered in high school, or perhaps earlier than that. First, let's make a copy of the sum, but with its terms in the reverse order. Notice that if you add the first two terms from both sums, you get n plus 1. The sum of these two terms is also n plus 1. It's also true for this pair, and so on, all the way to the nth pair at the end. Thus, if we add these two sums together, we get that 2 times Sn is equal to n times n plus 1. Now we just divide both sides of this equation by 2, and get our formula for the sum of the first n positive integers. Great! That was easy enough, but perhaps you would like to see a visual proof of this formula to get some intuition for what's going on. So let's dig into that. Okay, again, we have defined Sn to mean the sum of the first n positive integers. We can represent the first term in this sum with this one red dot. Then we add 2 dots next to it, representing the second term. This gives us 1 plus 2 dots in total. Also, notice that I changed the color of the text, as a reminder that the number of dots that we're looking at has changed. Anyway, now we add these 3 dots, representing the third term. Obviously, this gives us 1 plus 2 plus 3 dots, or 6 dots in total. So we can keep doing this until the column on the right contains n dots. Thus, the total number of dots in this figure is Sn, the sum of the first n positive integers. Also, notice that the row on the bottom contains n dots by symmetry. Of course, this particular figure that we're drawn illustrates the case n equals 5, but there's nothing special about the number 5 here. The arguments that we will see from now on will work for any integer n that's greater than 1. Anyway, let's make a copy of this triangular shape with Sn dots in it. Now we see 2 times Sn dots in total. That is, 2 times the sum of the first n positive integers. Now we rotate this orange shape and place it next to the red shape, like this, which gives us this rectangle. Clearly, the height of this rectangle is n dots, and its width is n plus 1 dots, so the total number of dots in it is n times n plus 1. So let's insert this into our equation. Then we just divide both sides of this equation by 2, which gives us our formula for the sum of the first n positive integers, again. Perfect. If we have a closer look at this rectangle, notice that the bottom row contains 1 plus n dots. This represents these 2 terms in the first green rectangle from previously. The second row from the bottom contains 2 plus n minus 1 dots, which represents the terms in the second green rectangle, and so on. So this rectangle of dots gives us a direct visual representation of our first algebraic proof. So by now you might be asking yourself, what does any of this have to do with salt? Well, to answer that, let's backtrack a few steps to our triangular shape with Sn dots. This time, we'll give yet another proof that Sn is equal to n times n plus 1 over 2, which I think uses a quite visually pleasing argument, and yes, it also makes use of salt. First, let's mirror these Sn dots horizontally, like this. This gives us 2 times Sn dots. Now let's mirror all of these dots as well, but we'll do it vertically this time. Doing so gives us this square-looking shape that contains 4 times Sn dots. Now, do you remember the images of salt that we saw at the beginning of this episode? Well, in the image to the right, we see a zoomed-in view of a sodium chloride crystal. Sodium chloride is, of course, the chemical name of salt. Specifically, the purple dots in this image represent individual sodium ions, and the green dots represent chloride ions. Also, the white connections between the dots illustrate the ionic bonds that hold this structure together. Furthermore, notice that every neighbor of a purple dot is a green dot, and similarly, every neighbor of a green dot is a purple dot. So, let's try a connection pattern similar to this one for our 4x SN dots. First, we connect each dot to its immediate neighbors in the left, right, up, and down directions, like this. Next, we'll color the dots in purple and green in this manner, so that each dot only has neighbors of the other color. Now, if we remove the chemical bonds, you can hopefully see that our pattern consists of two interlaced rectangles, one consisting of purple dots, and the other one consisting of green dots. We can observe these rectangles more clearly by separating these differently colored dots from each other. Also, notice that each of these rectangles consists of n times n+1 dots. In other words, the total number of dots that we see is 2 times n times n+1. So, let's insert this into our equation. Now we divide both sides of our equation by 4, which once again gives us our formula for the sum of the first n positive integers. So, that's it for this episode. If you enjoyed these little proofs, and would like to see similar proofs of other mathematical facts in the future, feel free to hit the like and subscribe buttons. Also, let us know in the comments what your favorite way of proving this formula was, or if you have another proof of it that you prefer. My name is Christian Hegg, and this is Mayday Mysteries.